Hi everyone, it's John. So today I'm going over the next worksheet, the second discussion worksheet. Hopefully this helps in preparation for your exam. So a lot of this is naming and shapes and geometry and that sort of stuff, along with some crystal field theory too. So this first part, we're getting into naming and oxidation states and coordination numbers. So for number one, we have hexamine, cobalt, bromide. The oxidation state that we're looking at is just the oxidation state of the transition metal. You do this just as you would or previously from 2A. You go ahead and you look at the overall charge of this, I believe it's called a coordination complex from Dr. Enderle's reader, but you look at this entire formula, you determine the charge of everything else, and then these are always going to be neutral. And then you determine the charge of the transition metal. So in this case, you have bromines, two bromines, each is a -1. Overall, there's a -2. All of these amines are 0. For this to be neutral, the cobalt has to balance out the charge, so this is a +2. The coordination number, in this case, it's just the number of ligand attachments. Not ligands attached, right? So that's two different things. So you're not counting the number of ligands, you're seeing it, how many attachments to the transitional do you have? So if you have a monodentate, each one gives one attachment. If you have a bidentate, each one has two attachments, right? Tridentate, I think that's what it is. Three attachments and so on and so forth. So here we do have just six monodentates. We have six ligand attachments, and we have a coordination number of six. That's it. Don't count the ligands. Make sure you're counting the number of attachments. Again, this will be apparent in a few problems. All right, for the next part, we have potassium and we have this complex ion. So the way you name this, it's kind of like ionic naming convention. So whether the complex ion is catatonic or anionic, you use typical ionic naming conventions for the other terms. So before we have bromide, which is what you would typically say, where bromine is the nonmetal in an ionic compound. And then here we have the metal potassium, which you usually just name, and we're just going to name it here. Great. So potassium, and then we do have to name the complex ion. So as a little list for how to name the complex ion, just the complex ion part. The first thing you do is you name the ligands that are attached in alphabetical order with their proper prefix. So bromo comes before fluoro, um, bromo comes before chloro, chloro comes before fluor, and so on and so forth. So you name the ligands. Then the next part is you name the transition metal. Then there is one kind of caveat here, where if the complex ion is anionic, or it comes second, you're going to add 8 at the end. Then the third part is include oxidation state with Roman numerals. All right, so to name this complex ion, we can just go down the list. The ligand we have here is fluorine. The naming convention for fluorine is fluoro. There are 6 of them. The proper prefix for it is hexa. So we have hexafluoro. Do you go alphabetically based off of the name of the ligand, not with the prefix? So something to keep in mind. And then we have aluminum. Now, because this is an anionic complex ion, we do have to add the 8 at the end. And so instead of aluminum, it's named aluminate. Okay. And then we can go to the oxidation state. The oxidation state, and we'll get the Roman numeral here too. Each potassium is a +1. There's 3. There's a -6 from the fluorines. Aluminum has to be a +3 to balance this out. The coordination number here is 6. We have 6 ligand attachments. Okay. Moving on, we have lithium. So we're given the name lithium tetracyanocuprate 2. So we have lithium, then the complex ion. Start with your transition metal in the brackets. So you start with your transition metal. Then we have the different ligands. So we have 4 cyano groups. And that's it. Now you have to go ahead and balance the charge here. So make sure you have the correct number of lithiums. So each cyanide is a -1. There's a -4. They tell us it's cuprate 2. So this is a +2, right? So from this complex ion, we have a -2. Each lithium is a +1. You need 2 lithiums to balance it out. The oxidation state, they tell us it's a +2. The coordination number here is 4. There's 4 cyano groups. They're all monodentates. Monodentate just means how many lone pairs they can donate to the transition metal. Okay. Next, we have this complex ion and then bromide. So for this one, we're going to name the ligands going through this list again. Name the ligands in alphabetical order with the prefix. So we have amine and bromo. Amine is alphabetically first. There is 4 of them. So we have tetra amine. And then we have 2 bromines, dibromo. Then we name the transition metal, since this is cationic, sorry. I think I wrote that wrong. Or I probably said it wrong before. I probably said catatonic, so cationic. My bad. We have dibromo chromium. Then we can find the oxidation state. So I'm going to leave some empty parentheses. And then we have the nonmetal, which is bromide. That's it. Looking at the oxidation state for this one, you do a little bit of math, you get a +3. So just as we did before, bromine is a -1, there's 3, amines are neutral, this has to be a +3. The coordination number here is 6. There are 6 monodentates attached, each giving 1 attachment or 1 bond. All right, going on, we start with, again, sodium, just as we did in the second one. Then we name the complex ion. So the ligand is oxalate. The name you name oxalate is oxalato. So this is tri-oxalato. Then we have the transition metal, cobalt. Now for cobalt, you add the 8 at the end because this is anionic. It's the second thing. And then we'll include the Roman numeral in a second. Oops, I forgot the Roman numeral up here. There we go. So the cobalt here, each oxalate is a -2. Each sodium is a +1. And so the cobalt here ends up being, actually, I messed up my math. The cobalt here ends up being a +2. So -6 + 4 is a -2. To balance it out, the cobalt is a +2. we have three ligands here. We have three oxalate groups. However, do be careful. You're not counting the number of ligands, you're counting the number of ligand attachments. So oxalate is a bidentate. It can attach at two places um, or donate two lone pairs. And so the coordination number here is 6, not 3. You're not counting the number of ligands. All right, next we're doing the same thing. We have sodium and then name the ligands. So for this ligand, it's sulfato. For S2O3, we have two. So we have disulfato. Then some of the transition metals have weird naming conventions. So silver is one of them. They use the Latin naming convention. It is something that you are just going to want to be aware of and memorize. So this is argon, and then we're adding the 8 at the end because this is anionic. And then silver is like always a 1, but you can double check it here. Double check the oxidation state, it is a +1. The coordination number here is 2. So sulfate, or sorry, the sulfato groups S2O3 are monodentates. They do have a -2 charge. The charge does not indicate, though, whether or not they're a bidentate or a monodentate. Often it can, but it doesn't always, so be careful. I recommend memorizing just the polydentates. So I think it's ethylene diamine oxalate, and then maybe EDTA you have to know, and then everything else is a monodentate. But again, just be careful with certain assumptions you may be making if you take a test or something. All right. Next, we have two platinums. We have two complex ions together. So this one's a little bit different, a little bit harder. For this one, what we can do is name them separately, and then we'll figure out the oxidation states in a second. So the first one, naming the ligands, the way you name water is aqua. So we have tetra aqua. Then you name the transition metal, platinum. And then I have a Roman numeral I'm going to figure out in a second. Then we name the other complex ion. There's 6 chlorines. This is hexachloro. And then platinate. And then we have some Roman numerals. Kind of all. Now, if you're looking at the transition, or sorry, the oxidation states here. So if you're looking at this whole thing, each chlorine is a -1. There's 6. So you have -6. Water is 0. So there's a +6 charge overall, but you have 2 transition metals here. So how do you do it? So something that is helpful is memorizing the common types of oxidation states for certain transition metals. So platinum is +2 or +4. So one of these is going to be a +2 and a +4, which will cancel out with the -6. Now, which one you pick actually does not matter. So at least in this problem. So the one you pick, because there's not really a way for you to know either. So the one I will pick here to be 4 will be the second one for no reason. You can also do it again the other way around. Like that. Then the coordination number for these, again, you're just kind of counting ligand attachments, it's 4 and 6. Okay, great. Going on to the next one, we have sodium diaqua dioxyl So we have sodium. I'll figure out how many I need later. I have iron. I have 2 waters. I have two oxalate groups, like so. So water is 0. The iron is a +3. They just straight up tell us. The oxalate groups are a -2 each. So overall, that complex ion is a -1. So we just need one sodium. The coordination number here is 6, right? Each oxalate attaches in two places, and then the water is a monodentate, attaches at one. All right, moving on. We have silver 1 tetraiodo mercurate 2. So we have silver. Silver is not part of the transition metal complex, right? That's just this thing. Or transition metal complex ion. Is a better word. Then we have our complex ion. It is mercury, like so. And then we have the ligands. We have 4 ligands of iodine. So you actually don't even need the parentheses here. I don't know why I did that. Or the tetraiodo. They tell us the oxidation state of the mercury. It's a +2. And the coordination number here is 4. Each iodine is a monodentate. Okay. Next, we have this kind of weird compound. We have nickel and then CO4. So in this one, we'll name it as if it were like the um, cationic version of a complex ion. Oops. So we name the ligands. There's 4. They're all carbonyls. These are all neutral. And then we have nickel. And then what is the charge here? So the charge is a little bit weird on this one. Each carbonyl is actually 0. So this is a 0 charge. So one's kind of the odd one out. The coordination number is 6, or 4, sorry, 4, just counting the number of ligands again. Then we have the next one. So I'm going to kind of speed through this one, right? It's very much the same thing. So we have iron, we have hexacyano. There are 6 CN groups, like so. The iron is a 3. Each cyano group is a -1. So we have -3 from the complex ion. We need 3 potassiums to balance that out. They tell us the iron is a +3. And the coordination number 6. Each cyano is a monodentate. All right, last one here. We have these ethylene diamine groups, and then we have the cyano groups. So the way you name the N group is going to be a little bit different than the way you name basically all the other groups. So for EN, there are some different prefixes that you have to use. So instead of di, tri, tetra, you use bis, tris, and tetrachus. I'm not sure why, right? It's just kind of the convention that was followed or that was established. So naming the first complex ion, and we only have one type of ligand. We have tris, so the special case for EN. And then the naming for it is going to be ethylene diamine. And then we have the iron. So the way you name iron is just iron. If it's cationic, it's different if it's anionic from what we saw before. Iron 3. Actually, we'll get back to that in a sec. So I'm going to leave an empty Roman numeral. And then for the second complex ion, doing much the same thing. This is hexacyano. And then we have ferrate. So the iron is named different, whether it's the cation or the anion. All right. So now if you're looking at the oxidation states, you have this one over here, and this one over here. ENs, this we have 6 cyano groups, each is a -1. The EN groups are all neutral. So we have a -6 charge overall, which means that both of the irons have to cancel out the -6. Iron has typical charges of +2 and +3. Both of these are going to have to be a +3 for it to cancel out. Otherwise, the charges don't cancel or neutralize. Coordination number here is 6 for both of them, and then it's done. All right. Going on, it says the structures of 4 complex ions are given. Each has cobalt as the central ion. The ligands are aqua, amine, oxalate, and oxalate. Current, which, if any, complex ions are isomers, geometric, or optical, which, if any, are identical, that is, have identical structures, and which, if any, are distinctively different. All right, so we have to go over a few terms here really quick. So the first thing is, what does it mean for things to be identical? So when two things are identical, what we say is that they are superimposable. The objects, in this case, the molecules, are superimposable. So you can line up every part of the object and place them on each other, assuming they were like intangible. So two things are identical. You can literally take them, rotate them around, whatever you got to do. But then eventually you have some type of conformation or way that you're rotating them where you can put them right on top of each other and they're exactly the same. So if you took a pen and you duplicated the pen would have all of the springs, all of the parts in the exact same spot, and you would be able to superimpose that pen. To give you something to contrast this to, because I don't think superimposability makes a whole lot of sense to some people, unless you contrast it. Unless you look at what optical isomers are. So if you have two things that are optical isomers, they are mirror images of each other, right? These are all relationships, so you have to have at least, if you're comparing two things to one another, you can't say something is identical to nothing else. That doesn't make sense. But they are mirror images of each other and not superimposable. Oftentimes these are called enantiomers, so those of you who take organic chemistry will see this name pop up quite a lot. So one example of like an optical isomer, I guess, or something where it has a mirror image, but it's not superimposable, is your hands. So if you take your hands, I guess assuming you have symmetric hands, but if you take your hands and you put them up to each other, you can see they're mirror images of each other, right? If I put my hand up to a mirror, it would look like my right hand up to a mirror, it would look like my left hand. Now, there's no way I can rotate my hands such that all of my fingers line up in the exact same spots and I can place them on top of each other, right? They're in opposite spots. My thumb is on opposite sides. My pinky's on opposite sides. I can't line my hands up and place them right on top of each other. So they, what you could say, are optical isomers. They are not superimposable on each other, right? So now you can kind of see the contrast. Where if I had two right hands, I don't, but if you had two right hands where you can line up everything, then they are identical. They're superimposable. If you have a left and a right hand, they are mirror images of each other, and you cannot put them right on top of each other. Okay. Then you have geometric isomers. Which is easy. You have same attachments or same ligands, but they're not identical. Or optical isomers. So if they have the same attachments and they're neither identical or optical isomers, then they're geometric isomers. Then the next part, or the last one, is if they're different, they just have different ligands. So it's like CH3 versus CH2O. They're just different. All right, so now we can do this problem. So looking at this problem, if you look at A and B, you may think, oh, look at that. They are mirror images of each other. So they are optical isomers. If you do this, you would be wrong. Why would you be wrong? Because remember the second part is they have to be mirror images of each other and not superimposable. So for A and B, how do you check if two things are superimposable? You rotate them around and you basically line up the groups that you can. And if they are superimposable, it'll be pretty clear once you line up two groups, I think it's two or three groups, everything else has to fall into place. And if they don't, they're not going to fall into place or line up, and they're not superimposable. If I were to go ahead and pancake flip B, I would end up with my NH3 groups over here. Oops. I would end up with my OH2 groups still on the top and the bottom because they're on the top and the bottom already. And then I would end up with my oxalate group over here. Now, this is exactly the same as A. So for that reason, A and B are identical because they are superimposable. You can line up every single group, and if I were to take one, I could stack it right on top of the other, and everything is exactly the same. This one you can just rotate 180 degrees. Like a pancake flip is what I call it. All right, so now we don't have to worry about comparing A or B, or A and B, I guess, to C and D because they're the same, right? So I'm just going to start comparing B to C because it's closer to make it easier, but we are talking about both A and B here because they are identical. So comparing B to C, we see that we have the same ligand attachments. We have two waters, we have, oh, whoops, no, sorry, I'm thinking D. So if you compare B to C, you have different ligand attachments. You have two waters and two amines on B. On C, you have one amine and you have three waters. So clearly these are just different, right? They don't have the same ligand attachments. I'll put A plus B. These are different. They're just straight up different structures. Now let's go ahead and compare B to D. Looking at them, they have the same ligand attachments. So you have two waters. You have two amine groups, and you have one oxalate group. So this checks out. Now, that means that these are either going to be identical, geometric isomers, or optical isomers. Has to be one of those. They're not different. They're not just straight up different. So how do you check? Right? How do you check if two things are geometric isomers or optical or identical? I think the easiest way is to check first whether or not they are geometric isomers. So if you check how you check for something to be a geometric isomer, I can put a little thing over here. You can ask or look and say, are ligands attached similarly on the axes? So what does that mean? So anyone who's just looking at the answer key may not know this, but if you're watching the video now, I will explain it. So what does that mean? Similarly attached. So actually I can write it out here. We can say ligands on the same axis, same ligands on same axis, not same exact axis, right? So when we're talking about axes, we're talking about these three axes. They don't have to be the same one of those axes, but um, just on the same axis. So I'll show you what I mean. All right, so looking at B and D. In B, we have water on the z-axis, but they share one axis. That's the important part here. In D, the waters are on two completely different axes. The axes again run through the center molecule, but they're on two completely different axes. So one is over there and the other is over there. And because they are on two different axes, they are geometric isomers. There is no way that you can rotate A or B to look like D. And it's because of the way they're oriented on these axes. You're never going to get the two waters to be side by side, right? They're always on the same axis opposite from each other. And indeed, the amines are always going to be on the same axis on opposite sides of each other. There's no way you can do it. So that is an easy way that you can do to check for geometric isomers. So we have A and D are geometric isomers. And then the last one is comparing D to C. We know that D and C are different. All right. So that is it for this problem. And we are going to use the same check in future problems as well. Now, if you want to check for optical activity in an isomer, there's a few things you can check. So the first thing is that only a tetrahedral or an octahedral complex can be optically active or be chiral. So that's one. The next thing is if it is a tetrahedral complex, all of the ligands have to be different. Otherwise, it's not optically active. So those of you who take OChem, you'll see very similar thing, carbon stereocenters. But that's one rule. And then for octahedral, there's a few ways you can do it to check if something is optically active. There is a nice list that I recommend you check out in page 52 of Dr. Enderle's reader. It's a small list and it's not exhaustive, but it is helpful in this problem and other problems, determining if something's optically active. Another way you can do it for an octahedral complex is you can draw the complex. I will not be doing that here, but you can draw it, draw the mirror image, and then see if you can superimpose them or not. And if you cannot superimpose them, then it is optically active. An optical isomer does exist. If you can superimpose them, then it's not optically active. The answer here ends up being A. So if you look, and we'll cover why the other ones aren't. But if you look at Dr. Enderle's reader, again, it's very helpful. You should all have access or equitable access. If you go to UC Davis and you're in one of the 2C classes. But One of the rules here that Dr. Ennerly says is that if you have two monodentate ligands that are the same and they are cis. Or another one is if you have two bidentate ligands in the cis position. Both of these are equivalent here. You have two bidentates and two monodentates. They will both end up being cis. And so the answer is A. You have two cis monodentate ligands. I should say identical ligands. Okay. So that's why that one works, and it has an optical isomer. For B, you have four well, you have four identical ligands, you have four amine groups. Then you also have two identical ligands. You have the two chloro groups. However, we don't know what the positions are, right, of these ligands. So if you have just some sort of mixture of these ligands, so this can exert a cis or trans isomerism, then we do need to know which one it is, right, to determine whether or not it's optically active. The same thing is true for C. For D, it's tetrahedral and all ligands are the same, so it's not optically active. And the last one, it's not tetrahedral or octahedral. It's a linear shape. So the answer here is A. Next, it says, of the following complex cations, which are identical, which are geometric isomers, and which are enantiomers, which are optical isomers. All right. So comparing these, we're kind of do the same thing. We're going to compare the things closest to each other just because it's easier. So let's compare A and B first. Right? That seems like a good start. So if we're comparing A and B, I'm going to use the same check first for geometric isomers. Or actually I should do the same check first to see if they're any different. So we do have two yellow ligands on both. We have two blue bidentate ligands on both. So these have the same ligands, so they're not different. So are they geometric isomers? So let's go from geometric isomers and then we'll check for whether or not they're identical or not. It seems to be an easier way to check. So we're checking if they're geometric isomers. Well, oops. I see here that I have this cis isomerism in B, right, where I have these two monodentates or these two ligands on two different axes that are right next to each other. In A, I have this trans isomerism where they're opposite from each other. There is no way I can rotate A or B to look like the other one because they're just on different, the ligands are on different axes. It's what it is. So for that reason, we can say A and B are geometric isomers. Now let's compare A to D. So A to D, just because they're close to each other. If we're looking at A and D, we see that we have the two ligands are the same. All the ligands are the same in all these, so I won't keep doing that. But we have two ligands on the same axis in A and D. So now why don't we go ahead and check whether or not these are superimposable. Well, if I took A and I were to rotate this up by 90 degrees, and this one goes down, and that moves down, right, and this moves up, then I actually would end up getting, actually not quite. I would almost get D. I would get an attachment where I get the yellows are on the top and the bottom, but then I would get the two bidentates like this. So not superimposable quite yet, but I have lined up the yellow ligands. Then what we can do is go ahead and rotate one more time. If I were to rotate this by 90 degrees. So this kind of flat plane in the center of the atom. If I rotate that by 90 degrees, then we do end up with D. So for that reason, A and D are identical because they are superimposable. So for this one, we would rotate up 90 degrees and right 90 degrees. And let me actually make this more clear. What we did was rotate A. All right. So that also means that D is a geometric isomer to B, because D and A are the same. Okay, moving on. Why don't we go ahead and compare A to C? So comparing A to C, we have two different types of ligand attachments once again. So it just has to be geometric isomers. Sorry, not ligand attachments, but two of the same ligands on different axes again. So differently attached. So we know that A and D must be geometric isomers to C. Right? Yellow ligands, two different axes, yellow ligands on the same axis. Then we can look at A and E. Again, two yellow ligands on the different axes. So A and D and E are geometric isomers. Right, again, we're just checking ligand attachments on the axes. We're seeing if they're on the same axis or different axes. Really easy way to check for geometric isomerism. All right, now we can do B. So if we compare B to C, if you try to superimpose B to C, what we would do is rotate that down 90 degrees. Then we would have the two yellow ligands here, which I'll shade in. Then we would have one bidentate like this, right? And then the other one like this, because that one didn't move, right? The atom in the back and the front didn't move. So now when you look at this, well, the two yellow ones are in place, but you can see that the way the bidentates are attached are different from B and C. The top one comes to the one in front of me. The bottom one goes to the one on the right in B, versus C, the bottom one goes to the one in front of me, and the top one goes to the one on the right. So they are not superimposable. So they are not identical. Now, they're not geometric isomers either. So what do we do? Or from what we can tell, sorry, from what we can tell, they're not geometric isomers from our test. Well, are they mirror images of each other now? So if they are mirror images of each other, we know they're not superimposable, so we know they're not identical. If I were to rotate this down by 90 degrees, and then to the right, I would have my yellow ones here. Yep. And then I would have one of my bidentates like this. That one goes up and there. And then the other two have to be like that. Okay, great. Now what I can do is if I pancake flip this 180 degrees, it ends up being the mirror image of C, right? Where this part is now down here. This part corresponds to the one up there, right? Where it's on this side, like that. And then these will be in the same spot, and so on. I actually messed up my drawing that second time, but the first time was right. And so when you rotate B around, you can see that B and C are optical isomers because they're mirror images of each other. To do your first easy check for geometric isomerism, you can even do like a check whether things are cis or trans or fash or mer. And then that's one easy check. And then you can also do this. All right. Then we look at E or B to E. I won't go through this one fully, but if you rotate down 90 degrees and then to the right, B and E end up being identical. And then we know E is also an optical isomer to C. And I have to now append all of these. That's E. Okay. All right, moving on to the next one. It says, which of these octahedral complexes would you expect to exhibit geometric isomerism? So there can be multiple answers here. So the first one, you would not expect there to be geometric isomerism because you have 5 identical ligands. You can draw it out if you would like. I won't here, but if you have an octahedral complex and 5 of the ligands are the same and one is different, no matter how where you put that ligand, you will always be able to superimpose it on another version that you draw or its mirror image. So there's not going to be, well, mirror image would be the optical isomer, but there's not going to be any geometric isomerism there. So you can't have 5 identical ligands. You also can't have 6 identical ligands in an octahedral complex for geometric isomerism. For the next one, this is a yes, because you have 3 identical ligands. So it can be Bash or Mer. So if you have 3 identical ligands, you can have a Fash or Mer isomerism. I guess to just go over the terms very quickly, I'll go over cis and trans first. So cis is where 2 ligands, and I'm actually going to just write IL. So I don't have to keep writing this. So if you have something that is cis, you have 2 identical ligands on different axes, so they're the same exact ligand. If they're trans isomerism, you have 2 identical ligands on the same axis. It's exactly 2. If it is Fash, you have 3 identical ligands on different axes. And if it's Mer, you have 3 identical ligands where 2 are on the same axis. And then 1 is on a different from the other 2. So that is just the terminology here. All right, so going into the next one, we have C. We have 2 sets of ligands. We have 2 identical ligands, 2 sets of identical ligands, actually. And so the answer here is yes. We have two identical ligands. So we can have cis or trans isomerism. This is most easily said or done with looking at the monodentates. So looking at the monodentates again, it's just an easier way to do it. You have two chlorines. Um, so those can be on opposite axes from each other. With B, the amines can be Vasher. Looking at D, the answer is no. So if I circle these, it's no because we have four identical ligands, or only four of the same ligands. So kind of running the same problem as A. And then the last one is no, not for geometric isomerism, at least. You have three identical bidentates or bidentate ligands. That doesn't mean it's not optically active, though. It just can't exhibit cis-trans Bash or more isomerism. All right. I should note here. These are monodentates. Then it says, which of the following compounds do not have Fash or more isomerism? So you're looking at the monodentates. You're seeing if you have three identical monodentates or not. So A, you have three identical ones. You have bromines. You also have three identical chlorines. So A can have Fash or more isomerism. B, you have three bromines. So this can have Fash or more isomerism. C, you do not have three identical monodentates. And D, you do not either. There's not three identical monodentates. Next one, it says draw a structure for cis dichlorobis ethylene diamine cobalt 3 ion. Is this ion chiral? And is the trans isomer chiral? So the way you can draw these, the convention is where you have probably seen you have the wedges, you have the dashes, and you have the up and down, like so. Now, the easy way to do this, to draw, if they give you the isomerisms, in this case, cis, draw in the isomerism first, right? And then everything kind of falls into place. So I'm going to draw chlorine as a cis isomerism. Like that, you could do it on different axes if you want. Doesn't really matter. So cis, two different axes, right? I just can't put it over here. Then I have to just draw my two ethylene diamine groups. So draw on some NH2s. Like so. And then we have to connect them. Now, the only way that reasonably makes sense to connect these is like that and like that, because I can't wrap this one around to the other side. I guess you could also do it like this, right? So connecting these two and then connecting those two, that would also be fine. Then you can draw the mirror image. So I'm basically just gonna draw a mirror. So same setup here, draw the wedges, draw the dashes. I have the NH2, the ethylene diamine closest here. I have the chlorine on top still, the chlorine in the back, and then I have the two other ethylene diamines over here. Great. All right. Then what you do is you check if they are superimposable or not. And the answer is no. So the easy way, I'm not going to do it here, but if you rotate this one around, you will find that they're not superimposable. So we'll say that putting chlorines in the same spot after rotation shows they are not superimposable because the bidentates, even though they'll be in imposable, even though they're not going to be in the same, or they will be in the same spots, they're going to have different attachments. So one may be attached to in one way, while the other one is going to be attached to different a different one in a different position on the complex, just as we saw before. So I'll leave that exercise to you to rotate it or try that out. And so because of that, this is chiral. Then for the trans isomer, the rule of thumb is that trans is never chiral. It's always superimposable. So the only ones that you have to worry about chirality is FASH or cis. Mer and trans will always be superimposable if you draw their mirror image. All right. So I'm not going to draw it here, but you can, and you'll also see that they are superimposable. And you can use the same rule, right? Draw out the cobalt and then draw the chlorines trans to each other. And then everything else falls into place. Next one is how many isomers are there of the complex ion? We have, oh, of that. Sketch the structures. All right, so way you can look at this is we have two sets of identical ligands. So what I can do or I should say two sets, sorry, of two identical ligands. So we can draw both in cis or trans isomerism. All right. So I'm going to go ahead and make a template here, and then I'm just going to start copying and pasting this since we got quite a few here. Okay. So the first thing I'm going to do is draw the chlorines in the trans position for no other reason than that's just how I'm drawing them. Then I have the two amine groups. You can put them on the other side. Doesn't really matter. And then I have my last one, the ethylene diamine group. Done. That's one. These are the chlorines when they're trans. Then I can also draw the one when the amines are trans, right? So that makes it easy. NH3, NH3, Cl, Cl, NH2, NH2, like that. Great. So now this is where the NH3s are trans. Next, what you can do is draw it when They are cis. Please paste. Not sure what's happening. So if I want the chlorine cis, I'll just draw it something like this. And then I'll have NH3 over here and NH3 down here. Like that. Now notice that both the amine and the chlorine is cis. Now, something I should also note on these other ones is that, so we can distinguish these. The Cl's are trans here, but the NH3s are cis. In this other one, the NH3s are trans, but the chlorines are cis. And then this one, both the chlorines and the NH3s are cis. So these are all geometric isomers to each other, right, so far. Again, just from before, from what we covered, you can look at where the ligands are attached and whether or not they're on the same axes or not. So in this case, I'm just using now cis or trans terminology to go along with it, but it really is the same idea. So both the chlorines and the NH3s here are cis, so I know it's not the same as either of these. Great. And you're basically gonna want to keep it like that. And then you can, since cis can have an optical isomer, you can draw the mirror image here. Now, if you have two things cis, it's a pretty safe bet they're not going to be superimposable. And in this case, they are not. Or two different types of monodentate ligands that are cis, chances are they're not going to be superimposable. And they aren't. So these are enantiomers or optical isomers. They are not superimposable. So you would actually want to check that if you're not sure. Again, the way I kind of checked, I didn't actually check, but if you try rotating this around, you won't get it. There's two types of cis monodentates. It's probably not superimposable, along with a bidentate. All right, going to the next one, it says, which of the following complex ions do you expect would absorb at the longest wavelength? So the way we can do this one is using this equation. And you're not going to actually plug in anything. But we have this. So energy is equal to Planck's constant times the speed of light divided by the wavelength. Now, you can solve this algebraically for wavelength like that. So looking at this, higher energy yields a smaller wavelength, and lower energy is a larger wavelength. Why? Well, if you look at this term over here, E is a fraction, in the denominator specifically of the fraction. So if you divide by a bigger number, you get a smaller number coming out. You divide by a smaller number, you get a bigger number coming out. So looking at this, what we are going to want, we're going to want the weakest field ligand. And the weakest field ligand here is fluorine. So between water, fluorine, cyano, and EN, if you check the list or your ligand list, you will see that F is the weakest ligand here, or the weakest field ligand. So weaker field is lower E. Okay, great. Next, we have to draw the d orbital splitting diagrams for the different octahedral complexes of the following. So we have high spin and low spin. All right, so the noble gas notation for iron. Iron 2 plus is that, where it's lost 2 electrons. Right, because it loses the 4s electrons first, and then you have that many left. All right, so looking at this, we have an octahedral complex. So our orbital diagram looks like this. With a high spin, you have a small gap in the energy. So what does that mean? What that means is that you can fill higher orbitals before you couple your electrons. So here we have 6 electrons that we need to put in this diagram. And we're going to just fill all of the orbitals up first before we couple anything. So spin up, I'm just going to do up, spin up, and then I go to a higher one. Basically, the gap in energy is so small that even though it is a higher energy, it's not big enough to need to fill the lower orbitals first. If it was a high enough energy gap, it would not fill the higher orbitals. Then if we do low spin, setting up the same thing, it's actually going to be the opposite. Low spin, and you have a large gap in energy. Right. Maybe you can even put this as delta E. So here we have a low spin and a large gap in energy. You fill the lowest orbital first, or yeah, before filling higher ones. So for this one, you still use your general principle. I think it's called Aufbau's principle, I think, or was it Hund's rule? But you fill the low orbital like that, and then you couple them together. There's 6 electrons. There we go. And then this is done. So high spin, there's a small change in energy, so it's not super unfavorable to fill higher energy orbitals. With a low spin, there's a large gap in energy. Kind of think about spinning a basketball or something. For spinning on your finger, the slower you're spinning it, the more likely it's going to fall off your finger. All right, going to the next one, we have iron 3 plus with high spin. So this is basically the same. So the noble gas notation for iron 3 plus is this. We have 5 electrons that we need to pair or fill in. And since this is just high spin, I'm just going to follow the same rule as before, where you fill up each orbital first. For nickel 2 plus, we're doing the same thing here. Actually, yeah. Oops. So the noble gas notation for nickel is this. If they don't tell you anything about spin, assume it's low spin. So if we assume it's low spin, again, setting up the diagram, we have 8 electrons. So you have a large gap, right? So we're going to fill up the bottom one first. And then we fill up the higher orbital. And then we're done. Going on to the next, we have zinc. Again, we're assuming low spin. The noble gas notation for zinc is this, for zinc 2 plus. If you need a reminder on noble gas notation, I think there's plenty of good videos online, so I recommend checking that out. Just remember that the electrons are coming away from the s shell, which is why we don't have s here with these ions. Oops, I forgot 2 plus here. Doing the same thing here. It's low spin, so the way we fill this out is bottom one first, like that. And then we have 4 left, and this ends up being full. Again, low spin, and this is true for low spin or high spin. You fill up all of them, and then you pair them. For high spin, you just fill up all the levels first, and then you pair them. For low spin, you just fill up the lowest level first, and then you pair them. For this one, you're doing high and low spin. The noble gas notation here for cobalt is this. So we have 7 electrons that we're going to have to fill in. We have a small delta E here. I'm just going to go ahead and write it out for the other. Okay. So high spin, small delta E between the two. We go ahead and we fill up everything first. And then we pair. So we get that. Then for a low spin, fill up the bottom one first, following our usual rules. And then we go to the higher one. Then this is it. For this problem, it says choose the correct shape, weak or strong field, number of unpaired electrons. So we have 6 ligands. So this is going to be an octahedral shape, or I should be more specific here. There's 6 ligand attachments or bonds. All right, because we have 6 monodentates here, all of the amines, so we know it's going to be octahedral. If you look at your chart for the types of fields for ligands, so you will see that NH3 is a strong field ligand. This is what you would get from the list. Also, if it's a strong field ligand, this means that you have a high gap in energy and low spin. So when we draw this diagram, and actually one last thing, so the noble gas notation for cobalt is this. If you need to review any noble gas notation, I recommend just looking up a video. Pretty easy. And I should say cobalt 3 plus is that. There's a lot of great videos online for that. All right, so drawing for the octahedral shape using this, we have low spin and high E. I just have to, oops, that was wrong. Keep in mind if you have a high change in energy or high gap in energy, you fill up the lowest row first, and then you pair it before moving on. If it's a low E, then you go through all of them and then you start pairing them. So we have 0 unpaired electrons here. It's octahedral and we have a strong field ligand. The next is for platinum, platinum 4. Platinum 4 plus. We have 6 ligands. So this is octahedral. We look at the list and we can see that Cl is a weak field ligand. Again, this list should be available to you. You should have it or it's in Dr. Enderle's reader. Then we can go ahead and draw this out. So since Cl is a weak field, we have a high spin or a low change in energy. So what we can do is fill up all of the spots first before we start to pair. So we have 6 electrons here. I fill up all the spots, that's 5, and then 6. So the answer here is octahedral, weak, and we have 4 unpaired electrons here. So just to recap, strong field ligands is a high gap in energy between filling the orbitals or a low spin. And then weak field ligands are the opposite, a low gap in energy or high spin. And then you can fill out your diagrams. Next is based on concepts from both crystal field theory and valence bond theory, the most likely combinations. We're doing the same thing here. Just as a recap for vocabulary, paramagnetic has unpaired electrons, and diamagnetic is no unpaired electrons. Okay. This is still octahedral, right? You still have 6 ligand attachments. The noble gas notation for iron 2 plus is this. So we have 6 electrons we need to fill in. Then water here, or the aqua groups. So the ligand is a weak field ligand. So we're going to have a high spin and a low gap, so we can fill in everything before we pair like that. Now you can see that there's 4 unpaired electrons. So this is paramagnetic. So the answer here is D. Going on to the next one. So the next two are, or next one is exactly the same. So I'm going to kind of speed through this one. Again, this is an octahedral because you have 6 ligands, 6 ligand attachments. Fluoride is a weak field ligand. The noble gas notation for cobalt 3, as we did before, 3d6, like we did before. Yeah. And then we can just go ahead, fill out our diagram. So this is high spin or a low gap in energy. So we're going to fill up all of them again. And then we pair. So again, this is paramagnetic. And the answer is once again D, octahedral paramagnetic. All right, moving on. It says in both iron, the iron aqua complex and the cyano iron complex, the iron is present as iron 2. However, one is paramagnetic or one is diamagnetic. Explain the difference. So this has to do with electron pairing, right? So one is paramagnetic because all the electrons are paired. And then one is diamagnetic because, oh, sorry, other way around. One is paramagnetic because not all the electrons are paired. One is diamagnetic because they are all paired. So water here is a weak field ligand. And the cyano group is a strong field ligand. Okay, so those are our diagrams. So doing the weak field ligand, again, high spin, low gap in energy. Strong field is the opposite. One, two, three, four, five, six. One, two, three, four, five, six. So you can see with the water, it is paramagnetic. And with the cyano groups, it is diamagnetic. So explain the difference. The difference has to do with electron pairing and having strong versus weak field ligands. And we know the strong field ligand is diamagnetic. And that's it. Oops, I forgot to erase this one. Right, so basically what happens up here is the strong field ligands force the electrons to pair before moving on to the next energy orbital. So because they're forced to pair, you're not spreading them all out where you get these unpaired electrons. Basically, if you have something that is low spin, or sorry, high spin or a low gap in energy, you would have to have enough electrons to fill up all the orbitals. So you would need 10 here. Otherwise, it's not paramagnetic. Next, we have this tetrachlorocuprate to absorbs light in blue parts of the visible spectrum, thereby appearing to have the color wet. So the way you figure this out is you look at the color that it absorbs and it shows the opposite color on the color wheel. So oh, my apologies. Audio cut out for any of those of you who are seeing this. So we're recording. So we look at the color wheel here. We have blue and it's opposite to orange. So if it absorbs blue light, then we see orange light. Or if it absorbs blue light, sorry, then you're going to see the color orange. The next says cyano complexes of transition metal ions, such as iron 2 and copper 2 are often yellow, whereas aqua complexes are often green or blue. Explain the basis for the difference in colors. So we can base this off of strong field and weak field ligands. That's the difference. So water is a weak field ligand. The cyano group is a strong field. So we can say cyano complexes are stronger field ligands. And let me actually write the equation here. So we used this one before, but cyano complexes are stronger field ligands. Or they have a higher gap in energy. Oops. Which means they absorb at a lower wavelength. And aqua complexes or have a lower gap in energy or a higher wavelength, right? Again, just look at the equation, dividing by a bigger energy. So in this case, it's E instead of delta E, but same idea. If you have higher energy, you get a lower wavelength. You have a lower energy, you get a bigger wavelength, right? Dividing by a smaller number. Then we say the cyano complexes absorb lower wavelengths because of the higher gap in energy. Then aqua complexes. So we see that cyano absorbs violet versus red and orange for aqua. How did I get violet? Right. It said that cyano complexes are often yellow. Well, if you see yellow, it absorbs violet. If you see blue or green, it absorbs red or orange. And when you look at this is true, right? So if you see yellow, you have a violet at around 4 absorption of violet light at 400 nanometers versus red and orange are at a higher wavelength, 620 to 800 nanometers. So that is consistent with what we're saying up here. That one absorbs at a lower wavelength than the other one. Right? Next, it says, and last one, it says match each ion with its expected color. So we have cobalt with a whole bunch of things. And then we get into that in a sec. So looking at the colors and the way when they absorb, again, you're just kind of looking at opposite on the color wheel. So green is opposite to red, blue is opposite to orange, violet is opposite to yellow, red is opposite to green, yellow, orange is opposite to violet, blue. It's like right in between. And then we put a dash. And then pale yellow is violet. Red, orange, yellow. All right. So looking at the wavelengths here, going from violet to red, it's increasing. Right? Violet's at 400, Red is around 800 nanometers. For the energy, it is opposite, right? It's inversely proportional to wavelength. So energy is increasing going downwards. Then we look at the complexes. So really what we're doing is going based off of ligand field strength. So we're going down in energy. So ligand let's file field strength. And it's increasing as we go down. Okay. So that's synonymous with the delta E. Okay. So now we look at this. We have the lowest energy ligand here, or sorry, lowest field, yeah, lowest energy ligand here is going to be the fluoride. So this is where you just look at the chart. So the lowest energy ligand is the hexafluoride, hexafluorocobalt, CO, cobaltate, F6, 3 minus. That is your lowest energy ligand from looking at the list. It's the weakest field ligand. Um, then we go into the next one. The next one here, that is the next weakest field ligand, is the one with waters. Now, the next one that we have to look at is we have a bunch of them with amine. So amine is a stronger field ligand than water. But we have one with chlorine, one with water, and one with just 6. So you're basing it off of the last ligand that's different. So looking at chlorine, water, and another amine. Well, amine is both stronger than chlorine and the water, so it will be further down than both. Comparing the chlorine and the water ligands, as we just said, amine is a stronger ligand than water, stronger field ligand than water. So, um, so the one with, oh, whoops. So the one with all the amines will be at last. Sorry, I meant to say chlorine and water. So looking at chlorine and water ligands, the aqua ligand, water is a stronger field ligand than chlorine. So because of that, the chlorine is going to be lower in energy. Then the water comes next. Again, because water is a stronger field ligand than the chlorine. And then the one with a bunch of amines comes after. Now, last but not least, we have our last one, which is very clearly the strongest one with all the cyano groups. And that is it. All right. I hope this video helps, and I'll see you in the next one.